discussed about the voltage and current variations for open circuit and short circuit two cases. So now today we are going to discuss about the reflection and refraction coefficients of the lines terminated with different types of conditions. Okay, we are going to find out the reflection and refraction coefficients of a line terminated with different conditions such as open circuit line, short circuited line, and T junction, a lump reactive junctions, like this. Okay, with the different conditions, by taking different conditions, we are going to find out the reflection and refraction coefficients. Okay, right. Let us first see the reflection and refraction coefficients of a line terminated through a resistance. Okay, so let us take one transmission line whose characteristic impedance is Z here. Okay, so characteristic impedance, or you can also say that surge impedance of the line, and this line is terminated by a resistance R here. Okay, so here this is the sending end, and this is the receiving end. At the receiving end, we are connected the resistance R. That means the line is terminated by resistance R, and the line characteristic impedance or surge impedance is Z. So for this line, we are going to calculate the reflection and refraction coefficients of the line. Okay. So it has been seen that in previous sections, whatever may be the value of terminating impedance, whatever may be the value of this terminating impedance, so whether it is open circuited or short circuited, so one of the two voltage or current waves is reflected back with negative sign. Okay, so if you see in previous class, so when there is a open circuit, so the voltage wave will be reflected back with the negative sign, and current wave will be reflected back with positive sign. Okay, so for a open circuit line, voltage and current waves, voltage wave will be reflected with a negative sign, current wave with positive sign. So if there is a short circuit at the terminal, so then current wave is reflected back with a negative sign, and voltage wave is reflected back with positive sign. Okay, so these two we were discussed in the previous class itself. So now whatever may be the impedance or terminal impedance, so whether it is open circuit, short circuit, so if you see here, one of the two waves is negative here. Okay, so whatever may be the terminal impedance, whether it is open circuit in the sense resistance is infinity, short circuit is in the sense it will be 0. Okay, when the resistance is infinity, it is open circuit. For open circuit case, voltage wave is reflected back with a negative sign, and current wave will be positive. So like for the other case, this is the current is negative and voltage wave positive, right? And these reflected waves, whether it is a voltage or current wave, so these reflected wave will travel back from the terminal of the line towards the source end. Okay, so in the same line here. Okay, so from the source end, you will be having voltage and current incident waves. So the voltage wave and current wave, these waves which are coming from source end are called the incident waves. Okay, so these two voltage and current waves which are incident waves will travel through the line. In the same line, the reflected waves also will travel, right? So when you consider the incident voltage and incident current, so then if you divide V by I, so you will get impedance of the line Z. Okay, so in similar manner, V dash I dash are the reflected waves. So then V dash by I dash you will give as these are the reflected wave, so they will be having negative sign. So here you can write this equation for a reflected wave. I dash is equal to minus V dash by Z, or you can also write like this also. So V dash by I dash is equal to minus Z. Okay, so whatever may be the condition here at the terminal, whether it is open circuit or short circuit, so either V dash is negative or I dash is negative. So any one of the two reflected waves is negative, so here you will get the negative sign. Okay, so I dash here I dash is negative, which is V dash by Z. Okay, now for this case, the line is terminated with some impedance, some resistance here. So it is not open circuited and it is not short circuited. Okay, so it is terminated with some resistance R here. So in such a case, there will be some voltage, which is voltage or current, which is transmitted through this resistance. Okay, so some amount of voltage and current waves, those two waves will travel through this resistance. So those voltage and current which are traveling through this terminal resistance are called the refracted or transmitted voltage and current waves. Okay, so the voltage waves which are flowing through the resistance, terminal resistance, those are called the refracted or transmitted voltage or current waves. Okay, so how many waves you are having? From source N, you are having V comma I. So V comma I waves, these two waves will travel towards the light. These waves are called the incident waves. Okay, these are the incident waves. Now at the terminal of the transmission line, so there will be some reflection will be there, right? So the voltage and current waves which are reflected are called the reflected voltage and reflected current. So those are represented with V dash I dash. Okay, so now if there is some resistance or inductance, whatever may be the parameter, so now here some waveform will travel through this resistance. Okay, so that means it is transmitted to the resistance here. So because of that reason, the voltage across this resistor is called the transmitted voltage, so which is represented with V double dash, and transmitted current I double dash. Okay, so transmitted voltage and transmitted current, or you can also say them as a refracted. Okay, refracted voltage and refracted current, which are represented with V double dash I double dash. Okay, so now here V double dash will be equal to V double dash by I double dash will be equal to R, you will get. Okay, V double dash by V double dash by I double dash will be equal to R here. Okay, right. So now you also know that this refracted or transmitted wave will be equal to the sum of incident wave and reflected wave. Okay, so what it means? So if you want to take a voltage wave, voltage transmitted voltage wave, so then V dash, V double dash is equal to V plus V dash. Okay, V here is the incident voltage wave, V dash is the reflected voltage wave. So if you take the current, then I double dash will be equal to I dash, sorry, incident current I plus I dash plus I dash. Okay, so the refracted or transmitted wave is the sum of incident wave and reflected wave. So if you take a voltage, V double dash will be equal to V plus V dash, and if you take a current, I double dash will be equal to I plus I dash. Okay, so here V double dash and I double dash are the refracted voltage and current waves which are flowing into the resistor R. When the incident waves are V1, V and I. Okay, so now from those relations, these following relations will hold good. Okay, if you take the V and incident waves, I will be equal to V by Z. If you take the reflected, then I dash will be equal to, reflected will be having negative sign. Okay, minus V dash by Z, and the refracted current is I double dash is equal to V double dash by R. Okay, you have to remember these equations now. Okay, these are the main equations from which you can derive the reflection and refraction coefficients. Okay, so as we know that I dash will be equal to I plus I dash and V double dash will be equal to V plus V dash from this condition. So using these two relations, we can derive, right? So what is I here? So sorry. So you take this equation. So 202 19 955 202. Hello 202 evarama. 202 అబ్బాయికి హోస్ట్ వెళ్ళింది, ఒకసారి అబ్బాయి హోస్ట్ ట్రాన్స్ఫర్ చేయమనండి. 202 ఎవరమ్మా? సో ఎనీవన్ రెస్పాండ్ ప్లీజ్. సో 202. సో అబ్బాయికి హోస్ట్ వెళ్ళిందమ్మా, పిపిటి షేర్ చేయడానికి రావట్లేదు. సార్ ఇది హోస్ట్ పోయింది, ఇది నెట్ డిస్కనెక్ట్ అయింది సడన్గా. Okay, right now. Okay, so in this equation, we are going to substitute these equations here. Okay, so that you will get this equation, and from this equation you can write v dash is be equal to v double dash minus v. So this equation we are going to substitute here. Okay, so that you will get this. So finally v double dash, what we are getting here is v double dash is equal to 2r by z plus r into v. Okay, so from this what you can say, so v double dash is equal to by z plus r, so which is multiplied with v. So now this coefficient here 2r by z plus r, this coefficient is called the refracted coefficient of for voltage wave. right? So this is a voltage. So refracted coefficient is nothing but V ratio of V double dash by V. So the ratio of V double dash by V is called the refracted coefficient of voltage wave. So which is equal to 2R by Z plus R. Okay, right. So now if you take the current wave, so now I double dash will be equal to I double dash, what you will get here is, so 2V by R plus Z you will get. So how you will get? So here, so from here, from this equation, I double dash will be equal to V double dash by R, and this V double dash will be equal to this value. Okay, so in place of V double dash, here you substitute 2VR by Z plus R, so that this R and this R will get cancelled. Finally, you will get 2V by Z plus R, you will get. Okay, so now here you take this Z as common. So now V by Z can, so now, oh sorry, so this same relation here we are multiplying and dividing with Z here, so that you will get V by Z into 2Z by R plus Z. Okay, V by Z here is nothing but I, incident current I. So now the ratio of incident refracted or transmitted current I double dash by incident current I, it is called the refracted or transmitted coefficient. Okay, that value will be equal to 2Z by R plus Z. Okay, so this is the transmitted voltage and this is the transmitted current. Transmitted voltage, if they were asked, V double dash will be is equal to 2R by Z plus R into V, and transmitted current is I double dash is equal to I into 2Z by R plus Z for the case of line terminated through a resistance, right? So now if you want to find out the reflection and reflection coefficients in the sense reflection voltage coefficient and reflection current coefficient, so then how you do that? Ayyo. Okay, sorry ma, my voice is in mute. So can anyone inform me up to what I completed previously? Anyone talk, please? So I didn't check that my mic is in mute. నేను ఇన్ ప్రీవియస్ ఎక్కడ స్టాప్ చేశానమ్మా? ఇక్కడేనా? హలో, ఓకే, right here I will tell from here onwards again. So in this equation we are going to substitute all these. So you know the I is v by z, I dash is minus v dash by z, I double dash is v double dash by r. Okay, these values we are going to substitute in this equation. Okay, so that you will get this equation. Okay, so now here in place of v dash from this equation, so v dash you will get here is v double dash minus v. Okay, so in place of v dash here you are going to substitute v double dash minus v. Okay, finally the v double dash what you are getting here is this one. Okay, now after finding the v double dash, so now you have to take this equation, which is I double dash is equal to v double dash by r. So in place of v double dash you are going to substitute this equation, so that you will get the I double dash will be equal to I into 2z by r plus z. Okay, so whenever you substitute this v double dash in this equation, initially you will get this equation 2v by r plus z. So now this equation, numerator and denominator, we are going to multiply with z, multiply and divide with z. Okay, so then after multiplying numerator and denominator with z, so you will get v by z into 2z by r plus z. Now this v by z, this is nothing but I. Okay, so I double dash in terms of I you will get here is I into 2z by r plus z. Okay, so now you got v double dash and I double dash. So v double dash and I double dash are called the transmitted voltage and current waves. Okay, this is the transmitted voltage wave and this is the transmitted current wave. Okay, so this transmitted voltage wave you can also call it as refracted voltage wave or refracted current wave also. Okay, 2 and 3 are refracted or transmitted voltage wave and current wave. So now let us see the reflection voltage and current waves. So to get the reflection voltage and current waves, so in place of v double dash you are going to substitute v plus v dash in equation 1. Okay, so here this equation, in this equation in place of v double dash we are going to substitute this equation. Okay, in place of v double dash you are going to substitute this equation, which is v plus v dash. So what you get, v plus v dash by z, r is equal to v by z minus v dash by z. Okay, so that the equation you will get here. Okay, so now from this expression you can write v dash as the, so v dash is equal to v into r minus z by r plus z. Okay, so this is v dash is nothing but reflected voltage wave. Okay, now to get the reflected current I dash, so this I dash is equal to minus v dash by z. Okay, I dash is equal to minus v dash by z, where you got here this from this one. So I dash is equal to minus v dash by z. So that is we are going to take here. So in place of v dash you have to substitute the v into r minus z by r plus z. Okay, in place of v dash here you are going to substitute equation number 4, so that you will get I dash is equal to minus v by z into r minus z by r plus z I. Okay, so that means you can write this equation as minus I into r minus z by r plus z. Okay, so now you got the reflected voltage and reflected current in terms of incident voltage and incident current. Okay, you see here equation 4 and 5 are the reflected voltage and reflected current. So on equation number 2 and 3, these two are the refracted or transmitted voltage or and transmitted current waves. Okay, so from this V double dash I double dash are expressed in terms of V and I. In the similar manner, V dash I dash also expressed in terms of V and I. Okay, so now from these four relations, you are going to write the expression for reflection coefficients as well as refraction coefficients. So now from those relations, the coefficient of refraction. So refraction, or you can also say call it as transmitted. Okay, transmitted coefficient also you can say, or coefficient of refraction. So if you take a current waves, okay. So if you take a current wave first, so what is the refracted current wave? This one. Okay. So from equation number 3, so this is the refracted current wave. Okay, so from this equation number 3, if you write the ratio of I double dash by I, so you will get 2z by r plus z. Okay, so 2z by r plus z you will get if you write the ratio of I double dash by I. So this ratio of I double dash by I is called the transmitted coefficient, or you can also say it as a refracted coefficient. Okay, so refracted coefficient for current wave is 2z by r plus z. Okay, so in a similar manner, from this equation you can write the refracted or transmitted voltage coefficient as V double dash by V. So V double dash by V is the refracted coefficient for voltage wave. So which is will be equal to 2R by Z plus R. Okay, so those we were written here. Okay, so coefficient of refraction for current wave is 2Z by R plus Z. Okay, and for voltage wave it is 2R by R plus Z. Okay, so this for current wave, this can be written as I double dash by I value, and for voltage wave this will be equal to V double dash by V. Okay, so similarly the coefficient of reflection for current wave will be you will get from this equation. Okay, so from this equation the coefficient of reflection for current wave will be equal to I dash by I. Okay, I dash by I is the coefficient of reflection for current wave. So from this equation, so here this is nothing but it is I. So now from this equation number 5, I dash by I will be equal to minus R minus Z by R plus Z. So this is the coefficient of reflection for current wave. And for voltage wave, coefficient of reflection is V dash by V. Okay, so this V dash by V from equation number 4, you can write it as R minus Z by R plus Z. Okay, so like this you can calculate the coefficient of reflection as well as coefficients of refraction for both current waves as well as voltage waves. Okay, so what is the case here? So it is the case that the line is terminated with some resistance R. Okay, so when the line is terminated with some resistance R, the reflection and refraction coefficients we were derived here. Okay, so after finding this, now you can extend this to another extreme cases, which are open circuit case and short circuit case. Okay, so now suppose here if you substitute R is equal to infinity, it will become open circuit, and if you substitute R is equal to 0, it will become short circuit. So for the case of open circuit, what are the reflection and refraction coefficient? For the case of short circuit, what are the reflection and refraction coefficient? Let us see. Okay, so reflection and refraction coefficient for a open circuited line. So for open circuited line, you know that resistance R will be equal to infinity. Okay, so in those four equations which are derived here, so in these four equations, this and this, so we are going to substitute R is equal to infinity. Okay, so that you will get the coefficient of refraction for current wave and voltage wave, coefficient of reflection for current wave and voltage wave. Okay, right. So we are going the coefficient of refraction for current wave will be 2z by, in place of R you are going to substitute infinity, plus z you will get. So from this equation, coefficient of refraction for current wave you will get, what you are getting here is 0. Okay, and coefficient of refraction for voltage wave, so from this equation you are getting here will be equal to 2. And coefficient of reflection coefficient for current wave is -1, and reflection coefficient for voltage wave is +1. Okay, so these are the reflection and refraction coefficients for a line which is open circuited. Okay, so first we were derived for a line terminated with resistance, then that resistance is replaced with infinity impedance, infinity resistance, then it will become open circuit. When R is equal to 0, it will become short circuit. Okay, for open circuited case, coefficient of refraction for current wave is 0, and coefficient of refraction for voltage wave is 2. And similarly, coefficient of reflection for current wave is -1, coefficient of reflection for voltage wave is +1. Okay, so similarly, you can observe for short circuited case. So for a short circuited line, this resistance will become equal to 0, right? So in this equation, in these four equations, you are going to substitute R is equal to 0, so that you will get the coefficient of refraction for current and voltage wave, as well as coefficient of reflection for current and voltage. So in these four equations, you are going to substitute the R is equal to 0 in case of short circuited case, so that you will get the coefficient of refraction for current wave will be equal to 2, and coefficient of refraction for voltage wave will be 0, and coefficient of reflection for current wave is 1, and coefficient of reflection for voltage wave is -1. Okay, this is how you can calculate the reflection and refraction coefficients for a short circuited case. Right here. Now let us see the same reflection and refraction coefficients if the line is terminated with a resistance which is equal to the characteristic impedance Z. Okay. So now you are going to consider a case where the line is terminated with one resistance R. That resistance value will be equal to characteristic impedance of the line Z, R. So in place of R, you are going to substitute Z here. Okay, so whenever you substitute R is equal to Z, so then the coefficient of reflection for current wave will be equal to 0, and coefficient of reflection for voltage wave will also 0. Okay, so both coefficients of reflection will be 0 here. So that means there is no reflected voltage and no reflected current waves are there when resistance of the line is equal to characteristic impedance. Okay, so you will be having only incident waves as well as transmitted waves only. Okay, all the incident voltage will be transmitted through this resistance. There is no reflection when the resistance of the line is equal to the characteristic impedance. Okay, so the coefficient of refraction for current wave is 1, as well as for voltage wave also it will be equal to 1. Okay, coefficient of refraction, or you can also say that coefficient of transmitted, or transmitted coefficient also you can say. Okay, transmitted coefficient of current wave as well as voltage wave is equal to 1. So when the line is terminated with a resistance which is equal to the characteristic impedance. Okay, so in this case you are not having any reflected voltage or reflected current waves. Okay, the coefficient of reflection current wave as well as reflection voltage wave. Both will be equal to 0 here. Okay. So when the transmission line is terminated through a resistance which is equal to the surge impedance or characteristics impedance, the wave does not suffer any reflection. So therefore, such lines you can also say them as infinite length lines. Okay. So if there is no reflection, such lines you can call it as infinite length lines, or you can also say them as matched lines. And the load which is corresponding to this is known as the surge impedance loading or natural impedance loading. Okay. Right. Next case. So now reflection and refraction coefficients of line which is connected to a cable. Okay. Here we are going to consider another case. In this case, the line is connected to a cable here. So Z1 here is the line impedance, line characteristic impedance, and Z2 is the cable impedance. Okay. So that means here in place of R, you have to substitute Z2, and in place of Z, you have to substitute Z1. Okay. Right here, one important point you have to note here is that, so whenever a traveling wave looks into change of impedance, it suffers the reflection and refraction. Okay. So this reflection and refraction of waves will happen only when there is a change in impedance in the line. Okay. Here line is terminated with cable. So then that cable will be having different values of impedance. Okay. When there is a change in impedance, so here you will be having a reflection as well as refraction. Okay. So in previous cases also the same. When the line is terminated with resistance, so that means resistance is changing here, impedance, right? So when there is a change in impedance, so then again reflection and refraction will observe. Okay. So for but for the previous case, if you observe, so R is equal to Z. Okay. So impedance of the line as well as the terminal resistance will be both are same. So there is no reflection, only refraction will be there. Okay. So now let us see for this case with the line connected to the cable here. So now, so Z you have to substitute Z1, in place of R you have to substitute Z2. Okay. So now from the previous equation which were derived for the resistance case, this V double dash will be equal to V into 2Z2 by Z1 plus Z2 you will get. Okay. For the resistance case, what you derived here is V double dash is equal to V into 2R by R plus Z. Okay, this is the equation what we derived for the resistance case. So here R is nothing but here Z2, cable impedance Z2, and Z here is nothing but Z1. So refracted voltage or transmitted voltage V double dash will be equal to V into 2Z2. In place of R, you have to substitute Z2. 2Z2 by Z1 plus Z2 you will get. Okay. Now, if you observe the impedance of overhead line and cable, approximately these values are 400 ohms and 40 ohms respectively. Okay. Now, if you substitute these values here, so what you are getting here is V double dash will be equal to 2 by 11 times the V. Okay. So that means a voltage wave which is transmitted into the cable will be having a very small amount of value. Suppose here the incident wave is 11 kV, let us say. So 11 kV voltage wave is traveling in the overhead transmission line. Now at here you will get the transmitted voltage wave into the cable. So this transmitted voltage V double dash will be equal to 2 by 11 into this incident voltage 11 kV. So that means 11. So then this 11 will get cancelled. So that you will get 2 kV. Okay. So that means, so whenever the transmitted voltage wave is at 11 kV in overhead line, when it goes to the cable, so that will be reduced to 2 kV. So that means the magnitude of the traveling wave is reduced here when the line is terminated with a cable. Okay, so this is most advantage when you use it in substations for protection. Okay, so that means it is about 20% of the incident voltage. Okay, 20% of incident voltage is traveling through the cable. So because of this reason, overhead line which is terminated with the cable in a substation. So if you take a substation here, so before connecting the overhead line to the substation equipment, you will generally use the cable. So one cable will be used between substation equipment and your transmission line, so that if the surges coming in the transmission lines are at higher voltages, whenever they go into the cable, they will be reduced to 20% of the incident voltage, so that the terminal equipment will be less affected by those voltages. Okay, right. So here one important note here is that, so while connecting the overhead line to a substation equipment through a cable, it is more important that length of the cable should not be very short. Okay, you have to connect some length of the cable which is sufficient. Okay, otherwise successive reflections will happen at the junction, which result in piling up of the voltage, and the voltage at the junction may reach the incident voltage. Okay, as I said before, so when the cable is connected to the line, so here the transmitted voltage should be will be 20% of the incident voltage. So but if this cable length is not sufficient, so if it is very short, in such a case, here piling up the voltage will happen. Instead of transmitting the voltage which is 20% of this incident voltage, so this total incident voltage itself will flow through this, so which is not advisable. Okay, you have to take care that sufficient length of the cable should be used between your transmission line and your substation. Okay, that is the important point you have to note here. Okay, right. Now let us take the another case. So reflection and refraction coefficient of line which is terminated with T junction. Okay, right here. So here we are going to take one T junction. So this is the transmission line. Okay, so at this here it is bifurcated here like a T. Okay, so it is like this, so like a letter T. So because of that reason, this line is called the T junction line. Okay, so this transmission line is having an impedance of Z1, and one line will be having Z2, another line it is Z3, and this Z2 and Z3 will be almost in parallel. Okay, so now a voltage wave V is traveling over the line with surge impedance Z1, and when this voltage wave V reaches this junction, it is observed that there is a change of impedance. So when there is a change of impedance, as we know, there will be some reflection and refraction will occur. Okay, so whenever this voltage incident voltage wave is observed, some change in impedance, reflection and refraction can be there. Okay, so now let us assume that V2 double dash and I2 double dash. So these two are the refraction voltage and current in this line, and V3 double dash and I3 double dash will be the voltage and currents for this line, second line. Okay, so now this Z2 as well as Z1, so these two will form a parallel path when you take the surge wave. Okay, so Z2 and Z3 will form a parallel path as far as the surge wave is concerned. So surge wave is nothing but incident voltage or current wave which is coming from here. So as far as these two concerned, so these two lines you can say them as a parallel lines. Okay, so when these two are in parallel, so the voltage across this will be the same as the voltage across this. So that means V2 double dash will be equal to V3 double dash, so which will be equal to V double dash you can say. So V double dash is the transmitted voltage. Okay, V2 double dash will be equal to V3 double dash, which is the V double dash. So this V double dash is called the transmitted voltage. Okay, so now from this you can write some relations. Okay, so now V and I here you are having, here will be having V2 double dash I2 double dash, so two waves. So here V3 double dash and I3 double dash. So now, so you know that transmitted voltage V double dash will be equal to sum of the incident voltage V and reflected voltage V dash. So this expression you know, V double dash is equal to V plus V dash, and I will be equal to V by Z1. So this I will be equal to V by Z1. Similarly, I dash is the reflected current which is having negative sign. So which can be written as I dash is equal to minus V dash by Z1. Okay, and I2 double dash here is the transmitted current wave in this line. So the transmitted current I2 double dash will be equal to V2 double dash by this Z2, and I3 double dash is the V double dash by Z3. Okay, V3 double dash by Z3 you can write. So this V2 double dash and V3 double dash is nothing but V double dash only. Okay, so in place of V2 double dash and V3 double dash you can write V double dash. So because of that reason, I2 double dash is equal to V double dash by Z2, I3 double dash will be equal to I double dash by Z3. Also you can say that, so refracted current I double dash is equal to incident wave plus reflected wave. Okay, I plus I dash you can write. Okay, so now in this bifurcated line or T junction line, what is I double dash? I double dash is the sum of these two. Okay, so in place of I double dash you can write it as I2 double dash plus I3 double dash. Okay, I is transmitted current wave I, and reflected current wave is I dash. The sum of I plus I dash is called the transmitted current wave I double dash. So this I double dash will be equal to sum of the current flowing through these two lines, which is I2 double dash plus I3 double dash. Okay, right. Now substituting the values of currents in this equation. Okay, so in this equation we are going to substitute the values of currents. So I dash, I2 dash, I3 dash. So all these values. So we are going to substitute all these values in this equation. So that what you can write here. So in place of I, V by Z1. In place of I dash, minus V dash by Z1. I2 double dash, V double dash by Z2. I3 double dash, V double dash by Z3 you can write. Okay, then the equation what we are getting here is the V by Z1 minus V dash by Z1, which is equal to V double dash by Z2 plus V double dash by Z3. You also know that V double dash is the sum of V plus V dash. From that equation, V dash can be written as V double dash minus V. So now, in place of V dash in this equation, you are going to substitute V double dash minus V. Okay, so then you will get this equation. So now from this equation, if you do some mathematics, so then finally what you are getting here is V double dash will be equal to this value. Okay, so V double dash is equal to 2V by Z1 by 1 by Z1 plus 1 by Z2 plus 1 by Z3. So this V dash V double dash is nothing but transmitted voltage wave. And if you write if you derive the reflected voltage wave in similar fashion, so then you will get here the equation as this one. V dash is equal to 1 by Z1 minus 1 by Z2 minus 1 by Z3 by 1 by Z1 plus 1 by Z2 plus 1 by Z3 into V. Okay, this is for the T junction, transmitted voltage, reflected voltage. Okay, so by using these two equations, you can also derive the equations for transmitted current wave I double dash, which is equal to V double dash by V double dash, the combination of this Z1 and Z2. So they may call it as parallel combination. Okay. In similar fashion, I dash also you can write it as I dash is equal to V by Z1. So sorry, V dash by Z1. So you substitute V dash here, you will get the value of I dash. Okay. From these two equations, you can also get the transmitted current as well as reflected voltage. Transmitted current as well as reflected current. Okay. And you can also write the coefficients. So V double dash by V is the transmitted coefficient for voltage wave. So V double dash by this V, if you bring this side, so then 2 by Z1 by 1 by Z1 plus 1 by Z2 plus 1 by Z3. This is called the transmitted voltage wave coefficient. Okay, or you can also say it as a refraction coefficient of voltage wave. Similarly, from this equation, V dash by V you can write, so which is called the reflected coefficient for a voltage wave. Okay, right. So now let us take the another case. Here the line is terminated through a capacitance. So when a line is terminated through a capacitance here, how will be the refracted voltage? What is the V double dash? Let us see. Okay, so now here the voltage wave, here we are going to take it as a DC voltage wave or DC surge you can say. Okay, let us consider the DC surge which is traveling over the transmission line. Then transmission line impedance will be Z, and the line is terminated by capacitance C. Okay, now here our interest is to find out the voltage across the capacitor. Right, voltage across the capacitor is nothing but refracted voltage. Okay, so now the refracted voltage of the line which is terminated by resistance. So when the line is terminated with resistance, the refracted voltage what we derived is the this one, V double dash is equal to 2 VR by Z plus R. Okay, so now in place of R you are going to take C here, that resistance is replaced by capacitance. So now while deriving the for the capacitance or inductance cases, you take the S domain. Okay, so the refracted voltage of the line terminated with C in S domain can be written as, so now in S domain this V double dash will become V double dash S, and 2 into in place of R C in S domain what you can write 1 by CS. Okay, in place of C 1 by CS you will write in S domain, that means R is replaced by 1 by CS. Okay, 2 into 1 by CS by Z plus in place of R 1 by CS you will get, and here V is the this voltage, so DC voltage, DC surge you can also say. So this in terms of S domain that DC surge can be written as V by S, this one. Okay, now you do some Laplace transform here, and finally what you are getting here is that V double dash in time domain will be equal to 2V into 1 minus e power minus t by ZC. This is the transmitted voltage or refracted voltage through the capacitance, or you can also say that this is the voltage across the capacitor. Okay, So now if you see in this diagram, so the incident voltage is a DC voltage or a step voltage like this. Okay, so and the voltage across the capacitor, what you are getting here, this one, so which is nothing but it is exponentially increasing like this. Okay, so similarly you derive